Okay, so take a second, pause it, and write this function down, and let's factor so we can see what's happening. My numerator, it looks like I can factor out a 7 and an x, so if I factor out a 7x, I'm left with x cubed plus 1. So here's a real test of your memory. Um, do you recognize this? Because it's not a sum or difference of perfect squares, not that we have a factoring formula for a sum of perfect squares, but for a sum and difference of perfect cubes, we do, and we're going to explore that in a second. It's like, what if we didn't remember how to do that? In the denominator, it looks like I have a 5 and an x in both, so I'm going to factor out a 5x, and that means I'm left with a 1 minus x squared. Now, I know I can factor 1 minus x squared, so I'm going to go ahead and write 5x. Now, if the constant is first, then the constant is first. Don't switch them up on me. So it's 1 plus x times 1 minus x. But let's talk numerator. Do these share any common factors? I know this can factor. Do you know it can factor, right? If I think about my denominator, it will equal 0 at 0, at negative 1, and at positive 1. If this equals 0 at any of those numbers, then it shares a common factor. I mean, obviously not x, because that's already factored out. So let's think about negative 1. Negative 1 cubed is negative 1. And positive 1, negative 1 plus 1 is 0, which means 1 plus x or x plus 1 is a factor of this. Yeah? So if I know x plus 1 is a factor of x cubed plus 1, I'm going to go ahead and put in my placeholders. Then I can either long division out or I can synthetically divide it out. So what do I need to multiply x by to get x cubed? That's going to be x squared. So x squared times x is x cubed. X squared times 1 is x squared. Subtract. And I'm left with a negative x squared plus 0x. Drag that down. What do I need to multiply x by to get negative x squared? That's going to be a negative x. Negative x times x is negative x squared. Negative x times 1 is negative x. I'm going to subtract, which changes the signs, and that becomes plus x plus 1. Those cancel each other out. And then what do I need to multiply x by to get x? That's 1. And then 1 times x is x, and then 1 times 1 is 1. Subtract, and I'm left with 0. So that means that this x cubed plus 1 can be rewritten as x plus 1 times x squared minus x plus 1. I don't know if you remember, but a cubed plus b cubed is a plus b, a squared minus ab plus b squared. So I told you that if this is plus, this is plus. Always opposite and then always plus, right? So a cubed plus b cubed, drop the powers, square this one, multiply it times itself, multiply them times each other, and then multiply this one times itself. So a squared, a times b, b squared. So x cubed plus 1 simplifies down to x plus 1 times x squared minus x plus 1. Now there's another thing to remember about this. X squared minus x plus 1 is the final factor. This times this is the final factor form of that. And if you try and solve this, remember, you won't get any answers because x cubed plus 1 is a cubic function shifted up 1, and it only crosses at negative 1. There are no other zeros. So this right here has no zeros attached to it, only imaginary roots, right? Which means no x-intercepts and no holes in the graphic associated with this. This is just hanging out. Okay, I don't know how much of that you remember, but anyway. If I were to think about like where do I have, well, first off, let's look at the denominator, right? 0, negative 1, 1. Numerator, 0, negative 1, no zeros. So are any of these shared? Yes, absolutely. 7x and 5x are just x's, right? And then x plus 1 and 1 plus x, same thing. These share a common factor in the numerator and denominator, which means that they're both holes in the graph. So in fact, we have a hole at 0 comma something, and we have a hole at negative 1 comma something, right? So we're going to have to figure that out. If I simplify this out, the x's and not the 7 and the 5, those are still there, and the x plus 1 and the 1 plus x, I'm left with 7 times x squared minus x plus 1 divided by 5 times 1 minus x. So this is what this function would look like without the two holes in the graph. Okay, so let's plug in 0. If I were to plug in 0, then what I would be left with is 7 times 0 minus 0 plus 1, so 7 times 1. And then 5 times 1 minus 0, so 5 times 1, so it's just 7/5. Okay. As far as negative 1 goes, let's plug in negative 1. So I've got 7 times negative 1 squared is 1. Negative 1 times negative 1 is plus 1, so that's 7 times 3, 21 over. And then 1 minus a negative 1 is 2, so 5 times 1 plus 1, that's 10, 21 tenths. Okay? Alright, now what I want to do is, well, I guess I could have already said domain, right? All real numbers except negative 1, 0, and 1. Or negative a, negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. Alright. I'm just going to be all over the place because who really cares? This and this we're taking care of as far as holes in the graph, which means this, as a lone factor in the denominator, has to be a vertical asymptote. So that means I have a vertical asymptote at x equals 1. Okay. Let's look at the intercepts. If I look at x-intercept is when the numerator and only the numerator equals 0. Well, the numerator equals 0 at the same time as that, so that's out. That's out. Those are both holes in the graph. This never equals 0, which means this has no x-intercepts. There are none. Okay? Alright. And then y-intercept, the y-intercept, let's see, y-intercept is when x equals 0, but when x equals 0, I've already identified that as a hole in the graph. So there isn't one. Okay. In behavior model, so now we look at powers. The most powerful term in the numerator is 7x to the fourth, and the most powerful term in the denominator is negative 5x cubed. Which means, technically, I would need to do a long division on this in order to find the in behavior model. What we're going to do is we're going to say the in behavior model is basically y equals 7 divided by negative 5 is negative 7/5, and then x to the fourth divided by x cubed is x. So it's basically negative 7/5 x. It's not exactly. It's not accounting for a horizontal shift up and down. So when I think about a negative linear function, they start from above and go down below. So as x goes to negative infinity, f of x is going to positive infinity, and as x goes to positive infinity, y is going to negative infinity. And let's see this play out. So I've got 7x to the fourth. No, just kidding. Well, whatever, I'll just do it. 7x to the fourth plus 7x. Oh, dadgummit. Divided by 5x minus 5x raised to the third. Okay, I'm going to do a standard window, negative 10, 10. Okay, so here's what I know. I know I have a vertical asymptote at x equals 1. Cool, I can see that. I should have two holes in the graph at 0, 7/5, so I'm going to go ahead and zoom in on that. I'm going to go negative 1 to 1. And 7/5 is 1 and 2/5, so 1.4. So we're going to go 1 and 2. And we're going to go by 0.2. So it should be at the second on the y-axis. Oh, I can't see it because, just kidding, because the axis is in the way. If I do format grids off. Oh, axis off. There we go. Okay, so I took off the axis, and then you can see hole in the graph. Okay? I'm going to change that just so I don't forget. And then the other one is at negative 1, so we're going to go negative 2 and 0. And so I'm zooming in on the x at negative 1, and then I need to zoom in on the y at 21 tenths, which is just above 2, right? So we're going to go 1.5 and 2.5. And we'll go, that's fine, we'll just go keep it at 1. So this is negative 1 right here, and this is just above 2. And there we go. Okay. And then an in-behavior model is that negative linear function, so we can see that it does follow the negative linear function in the ends. Even though it's got some wiggling stuff in the middle, in the end it follows a negative linear with a slope of -7/5. Okay, cool. One more. Pause it for a second and write that down if you'd like. Now let's do this. The numerator does not factor, so there we go, 2x plus 5. The denominator looks like a difference perfect square, so I'm going to factor out a 4x squared. And I would be left with, so if I group these two with a plus sign in between, right? I would be left with x minus 1. And if I factor out a -25, then I would be left with an x minus 1. If I factor out an x minus 1, then I would be left with 4x squared minus 25. And that is a difference perfect square, so that would be x minus 1. So 4x squared minus 25, those are both perfect squares, so 2x plus 5 and 2x minus 5. Cool. The denominator equals 0 at 1, -5/2, and +5/2, and the numerator equals 0 at -5/2, which is a shared factor with that, but we'll go ahead and do domain. So all real numbers except -5/2, 1, and +5/2. Okay. The shared factor means that that's a hole in the graph, right? So I'm going to simplify that out and just think there's a hole in the graph at -5/2. Okay. Ooh, I need to figure out where that is, so I'm going to have to plug in -5/2 into what's left over. So what's left over is 1 over x minus 1 and 2x minus 5. So 1 over -5/2 minus 1, and then 2 times -5/2 minus 5. So let's simplify that. -5/2 minus 1, 1 is 2/2, so that's -7/2. And then 2 times -5/2 is -5, -5 minus 5 is -10. -10, that's 70/2, so 35, or I could see it as 10 divided by 2 is 5. And so either way I get 1 over 35. Remember, don't be afraid of the math. Okay? You can do it. Okay, so I found the hole in the graph that dealt with this one. That is taken care of because it was part of the hole. This right here, these are 0 in the denominator and only the denominator. That means they're vertical asymptotes. So x equals 1 and x equals 5/2. X-intercepts, well, there's no other term in the numerator. So remember, x-intercepts is when the numerator and only the numerator equals 0. So there are none. Y-intercept, I think we do have one because that's when x equals 0, and I haven't claimed x equals 0 for anything else. So if x equals 0, let's go up here, cover up everything with an x in it because they're all 0, and I'm left with 5 divided by 25, so that's 1/5. Okay, in behavior model, the most powerful term is in the denominator. So if I think about this, we're talking about 2x over 4x cubed, which means we have a horizontal asymptote. If the higher power is in the denominator, then the denominator is growing faster or larger, which means the number is getting smaller and smaller, and so small it gets close to 0, which means these two limits are 0. And that hopefully is enough to get you through the second part of this lesson. Okay.